Here's Chemistry Paper 1. Use the periodic table to deduce the electron configuration of calcium. It's got 4 shells, it's in group 2, so it's got 4s2, and it's got a backfill of 1s2, 2s2, 2p6, 3s2, 3p6. An ionic equation with state symbols to show the reaction of calcium with an excess of water. So it's going to make hydrogen, as metals do with water. It's a solid, water's a liquid, you'll need 2 waters to balance it, and calcium ions are Ca2+, aqueous, they dissolve as ions do in water. 2+ because they lose 2 electrons, you make 2 OH-, aqueous hydroxide ions. Hydrogen is H2 and it's a gas. Well, calcium has here been oxidized by the water. It's gone from an element, Ca, to Ca2+, so it's lost 2 electrons. In doing so, it's gone from oxidation state 0 to 2+, so the water is an oxidizing agent, it's causing it to be oxidized. Write an equation to show the process that occurs when the first ionization energy of calcium is measured. The thing that most people forget is that the calcium needs to be in a gaseous state, so it's Ca G gaseous going to Ca1+, because it loses 1 electron, that's the first ionization energy, and 1 electron comes off. As you go down a group, the first ionization energy down group 2 decreases because the ions get bigger. So as the ions get bigger, there are more electron shells, there's more shielding, and there's weaker attraction from the nucleus to the outer electrons because they're further away from the nucleus. Okay. You've got 3 isotopes. The first part of the question is to work out how much of the third isotope you've got. So you've got 100% of the isotopes, take away 91% for this isotope here, take away 1.8% for this isotope here, means that the third isotope is 7.2%. Now here, you could either divide by 100, or you could have 32 times 91, that's the percentage, so that's the mass of this isotope, 91% of it, times 33, that's the mass of this isotope, times 1.8% of it, and then the third isotope, well, you don't know what mass it is, so I've called it Y, times 7.2% of it, divided by 100. Or you could say 32 times 0.91, 33 times 0.018, and Y times 0.072. You could have divided them and have fractions out of 1 instead of out of 100. And it equals the average mass, so that's the average value when you multiply them all up. So if I rearrange that and multiply them all out, then 7.2y equals 32.16 multiplied by the 100. Take away 32 times 91 from here. Take away 33 times 1.8, so they've gone over to the other side of the equation, and it equals 244.6. So y is 244.6 divided by the 7.2 is 33.97, and y is 34. Describe how ions are formed in a time of flight mass spectrometer. Well, a sample is bombarded by high energy electrons from an electron gun, and the sample loses an electron. So if the atom is, say for example, M, it becomes M+, so M is a representation of the symbol for an atom, M standing for molecule. So the sample loses an electron and forms a 1+ ion, you could say it that way as well. Explain why it is necessary to ionize molecules when measuring their mass in a time of flight mass spectrometer. Well, there's only ions and not molecules. They've got to be charged if they're going to be accelerated by an electric field through the mass spectrometer. And only ions will create a current because it's the ion that attracts or takes electrons from the plate. And it's the taking of electrons when the ions turn back to atoms that generates a current on the plate or the detector. Write an equation including state symbols for the enthalpy change when a standard enthalpy of formation of CF4 gas. Well, I've made CF4 gas, and when it's enthalpy of formation, it needs to be elements in their standard states. That's as you'd normally find them in the laboratory at room temperature. Well, in there's carbon and there's fluorine. Carbon is a solid, so S, and S for solid, carbon solid, and 2F2. Fluorine is in group 7, wants to gain an electron, so they pair up in twos to each gain an electron by using a covalent bond, and I'll need 2F2 to make the 4F on the right hand side, and of course the gaseous, because fluorine is a gas. Explain why CF4 has a bond angle of 109.5. It's because there's 4 bonding pairs. Every fluorine wants to gain 1 carbon in group 4, wants to gain 4. So CF4 has 4 bonding pairs. All 4 electrons on the carbon atom are used up in the 4 bonds. There's 4 bonding pairs, and they repel equally and get as far apart as possible, and that creates a bond angle of 109.5. If you've got an enthalpy change here, then the enthalpy change, delta H, the heat change or the enthalpy change, is the total heat of formation of the products, take away reactants. So what I'll do is delta H equals minus 2889. It tells me that in the question here. So delta H, the heat change, is minus 2889, and it equals the enthalpy of formation of the products, take away the reactants. So the products are 2 lots of CF4, so 2 times 680, add 6 lots of HF, so 6 times minus 269, take away. Well, we don't know the enthalpy of formation of the products, of the reactants rather. It's this that we want to find. Well, I know that F2 is a molecule. You can't form it from anything. It is an element, a molecule with just one symbol in it. So the enthalpy of formation of that is 0 because I don't make it from anything. So I can call this X. So it's take away the enthalpy change of the reactants. That's 0. Let's call that X, so take away X equals that. When you solve it then, it equals minus 85 kilojoules per mole. For a bond enthalpy question, then you can say that the bond's broken, i.e. the reactants get their bonds broken. On the right hand side they get their bonds formed. Another way of doing it is, instead of bonds broken, take away bonds formed, which one way of looking at it, I sometimes say burp bond enthalpy, that's the bond enthalpy that we're trying to work out, equals the bond enthalpy of the reactants, take away the bond enthalpy of the product. So bond enthalpy BERP. So it equals the bond enthalpy of the reactants, take away the products, or you could say bonds broken, take away bonds formed, and the bond enthalpy of the reactants. The reactants are CH4, so there's 4 lots of that, so 4CH. Reactants 4F2, so there's 4 lots of F2. And that equals 4 times 412, add 4 times F to F bond. We don't know that, that's what we're trying to work out in the question. Bonds formed, or bonds in the products, so are CF, 484, and we make 1 lot of those, and HF, we're making 4 lots of HF, that's 4 times 562, and therefore the enthalpy change minus 1904 equals the bond enthalpy of the reactants, sometimes called the bonds broken because they need to be broken. Here is all of this, take away all of this. So it equals 4 times 412, add 4 lots of F to F bond, we don't know that, take away 4 times 484, add 4 times 562. When you rearrange it so that the 4FF equals all of this, it equals 632. F to F is one of those, so 1/4 of those divided by 4, and it comes out as 158. That's much lower than any of these bonds, so the question is the student correct? Suggested that the high reactivity of fluorine gives a weak F to F bond. Yes, it's a very, very low value, 158 compared to some of the others, so the student was correct. X and Y react to form an orange solution of Z here. Deduce the amounts of X and Y at equilibrium. Well, what you've got is, you've started off, a student had a solution containing 0.5 moles of X, so you've got 0.5 moles of that to start off with, and 0.5 of Y, and none of that to start off with. So there's 0.5 of that and 0.5 of that, makes none of that to start off with. At the end it says there's 0.2 of Y, so it must have used up 0.2 of this, and 2 lots of 0.2 of this, it must have used up 0.4 of this. So we start off with 0.5 of X, we've made 0.2 of this, so 0.2 of X must have been used up. I've ended up with 0.3 of X left over. Y, we start off with 0.5, 2 moles of that makes 1 mole of that, so I've made 0.2 moles of this, I must have used up 0.4 moles of this. So 0.5 take away 0.4 is 0.1. On the grid below you're looking for a line that goes up like this and then starts to flatten off. So it comes from 0, the x-axis is going to be time, and the y-axis is going to be the amount of Z that's made, the concentration of Z that's made, or the number of moles of Z that's made, up the right hand, up the y-axis. It's got to be large enough to cover at least half the graph. The mark starts at 0 because there's none of Z made at no time, but as the time goes on, maybe about halfway through, something like that, it might start to flatten off, and it ends up as 0.2 moles on this axis here, where the number of moles of Z that are made ends up as 0.2, and it'll flatten out at 0.2 because it tells you 0.2 of Z is made.